Well, here we are, chapter 21, the last chapter in the book. This will cover nuclear chemistry, and then I have some additional notes that I want to give you that are not in your book about medicinal chemistry. First of all, we'll talk about what we have in the book in chapter 21. Essentially, what this chapter covers is the structure of the nucleus and the stability associated with it, depending upon how many protons and neutrons there are. The nuclear equations, how you shift from one type of material to another type of material. Radioactive decay and the transmutation, and a special note for those in the medical field are the use of radioisotopes, and also the biological effects of radiation. So, nuclear chemistry provides the basis for many useful diagnostic and therapeutic methods. One of the things that they talk about is that when you have a cancer, that you can either burn it, or you can poison it, or you can cut it. The poison, of course, has to do with the chemical approach, the anti-cancer agents, but the burn usually refers to different techniques using X-rays or other type of high powerful rays in order to burn away the tumor. But here you can see the difference between the lungs of a smoker versus a non-smoker, and I think this has to do with the brain of an alcoholic versus a normal individual, and just different portions of the body that you can look at. And so let's talk about the nucleus. As the number of protons increase, in other words, you get further and further along in the periodic table, the number of neutrons also increases as well. And if you have those along this type of a path right here, these will be non-radioactive. If you have more protons than the number of neutrons, you can see that you're going to end up with a lot of different radioactive elements. And as a matter of fact, throughout this entire range up here, everything is a radioactive element. So you notice that all the isotopes with atomic number greater than 83, that's right here, are unstable. The solid line is where N equals Z. Okay, so this would be your number of protons, Z, equals the number of neutrons, N. So you see that you have to have quite a bit more of the neutrons as you get more, as you would expect, because you've got the high number of positive charges there, and the neutrons help hold it together then, so that they don't repulse each other too much. Now, the binding energy per nucleon is the largest for nuclides with a mass number of approximately 56. That's 56 is about where lead is. Okay, so when you have very high ones, what happens is they will decay radioactively, and they will form smaller ones. They break up as they go this way. Fusion is when you join them together and they move up in this direction. Okay, so fusion is the joining together of the nuclei. Fission is the breaking apart of the nuclei. Now, what happens? First of all, in these symbols you have an alpha particle, and that is He, the helium. So you've got four nuclei, four things in the nucleus, and two of which are protons. This is also represented in this manner right here. It consists of only the two protons and two neutrons. It does not have any electrons in it. Okay, so this is a +2 charge. A beta particle is essentially a high energy electron. And so it has -1 in terms of a charge. So it does not have any protons at all, and no neutrons at all. Okay. Positron is particles with the same mass as an electron, but with 1 unit of positive charge. The proton, we know about what that is. That's essentially a hydrogen ion that you have there. A neutron is symbolized with this, an N with 0 protons and 1 for its atomic mass. And a gamma is a very high energy electromagnetic radiation. So, but these are the words that we will talk about. These are the symbols that we talk about, and this is what they actually represent. Now, when you have radioactive decay, you've got a parent molecule here of uranium-238. When it undergoes alpha decay, in other words, when it undergoes fission by breaking it apart, it forms a thorium nucleus of 234 and gives off an alpha particle. So you can see you've got with this one, you've got 2 protons, those are the green ones, and 2 neutrons, which are the gray ones. And you can see that how you have so many more gray ones surrounding the different green ones to help stabilize this one. But nevertheless, it still will break up and give off this spontaneously. Now, alpha particles are attracted to the negative plate. Okay, this one down here. So alpha would be going down here. The beta particles, because they're negatively charged, will be attracted towards the positive plate. And so that in this photographic plate, you've got the beta rays that will appear up this way, alpha rays down here, and the gamma rays will go straight to it. Okay, they're unaffected by the electric field. They're uncharged. And so the equation are the following. Whatever that element is, with its number of protons and its number of total nuclides, protons and neutrons present, gives off a helium ion, an alpha particle. A drops down by 4, Z drops down by 2. Okay, so the changes in mass number and atomic number are the following. Atomic number decreases by 2. So that means it has changed material. This is the elemental change. And this decreases by 4. Here on beta decay, what happens there is, again, the total atomic mass is not changed, but the number of protons increases by 1. Okay? Gamma decay, neither the atomic mass nor the atomic number are changed. Positron, here you have the atomic mass unchanged, and this decreases by 1. And here it's unchanged, and this decreases by 1 as well. This is electron capture. So positron emission and electron capture work to be the same thing. Okay? But these are the equations that you go about, where essentially what you're doing here is substituting these, the element itself in for the X, putting what its numbers are, and then from that you get what you're going to have on the other side of the equation. So it has to balance. Only here, unlike all the other chemical equations we talked about so far, here you are changing what the element is. PET is a way to use radiation to give an image of how a person's body functions. And you have a healthy brain or medical condition of Alzheimer's disease. And this is one with Alzheimer's disease, whereas this is the healthy one over here. Now, uranium-238 undergoes radioactive decay in a series of 14 separate steps. Okay, so you start off up here, U-238. First, it drops down to thorium with the emission of an alpha particle. It goes to palladium. Okay, the atomic number hasn't changed, but the atomic number changes. However, the overall weight does not change. So that's a beta emission. And then you have it going up to uranium, so another beta decay. Then it drops back down here with another alpha particle, another alpha particle, another alpha particle. And so you can see it keeps on dropping in that manner. And so that finally what it ends up with is lead. 8 steps, 8 alpha decays, 6 beta decays to get from here to here, and a very, very long time for that to take place. Okay? How long it takes to get there, each one of these has something called a half-life. So for how long it takes it to get from this point to this point naturally. And then how long it takes to go this way and then following on down this way. So what you will end up with every single time when you have a radioactive material, the end point where it's going to end up is going to be with lead. Here's cobalt. Cobalt-60. This introduces the idea of the number of half-lives. If you start off with a 100% or 10 grams, and the half-life is 5.27 years. So after one half-life, or 5.27 years, it now has half of the mass. So it's gone from 10 grams down to 5 grams. Okay, 50%. The next period, the same unit of time, is going to go from 5 down to 2.5. Then the next period of time, it goes from that to half of its value, 2.5 to 1.25, right? So this right here would be 5.27. This would be 10.54, et cetera, et cetera, et cetera. This would be the 15.71, no, 81, and continues on that way, okay? So each one of these increments right here is 5.27 years. Each one of those, so it's the same length of time. Each time it drops by half. And so you can see it. Does it ever get to 0? Well, it gets close down there. So it takes quite a bit. After 15.81 years, 3 half-lives, there's only 12.5% remaining. And it just keeps on going. Along with stable carbon-12, there's also radioactive carbon-14 that is taken up by plants and animals, and it remains at a constant level within them while they're alive. After death, then the C14 decays, and the ratio of C14 to C12 decreases. So by comparing this ratio, and living organisms allow us to determine how long ago an organism lived and then died. Okay, so that is the use of radiation detection there. Now, carbon-14 data has shown these pages on the Dead Sea Scrolls were written or copied on paper from plants that died between 100 BC and AD 50. So it's quite a while, quite a range in there for these things. It's 150 years. And also what you can do is, for non-biological ones, non-carbon, you can take something that was dated with such as a coin. That is a very specific date on it. Or it could be something from the tomb of someone when you know when they died, from other records, other written records. So all of those things are based upon things which we learn from history and from. So one thing about any of this radioactive dating is you have to know what your initial amount always was. And that's the end of this first section.